Welcome everybody, it's Ramchandra from CIVIL-MECH-MATHS-CONCEPTS channel, and in this short video of about 40 minutes I will be discussing about fluid mechanics 3, lecture number 3. I have already released 2 lectures on properties, fluid properties. In this again I have continued on the fluid properties, especially I dealt in detail about the pressure at a point, pressure units, and also compressible and incompressible fluids, and also atmospheric pressure. Please listen to the lecture till the end. Pressure is very important topic in fluid mechanics which should be understood without fail. All the concepts of the pressure are to be understood. In the next lecture I will be taking up pressure measurement, which is also very important topic, and which we get many questions on SSC JE, RRB JE, GATE and CSIR examinations. Best of luck to everybody. Welcome to my channel CIVIL-MECH-MATHS Concepts. It's Ramchandra again. Thank you. Good morning everybody. It's Ramchandra from CIVIL-MECH-MATHS Concepts channel, and it is the third chapter or third lecture on fluid mechanics, and I am dealing with properties for the last 2 lectures, and it is the third lecture on properties of the fluids. It's very important. It's important in the examination point of view and also in the point of view of understanding the fluid mechanics in the following classes. And this lecture is for SSC JE, civil and mechanical engineering subjects, and it's not only for SSC JE. This lecture will be useful for GATE, CSIR and also UPSC, RRB JE and other PSC assistant engineer examinations. And in the first 2 lectures I had discussed about pressure. Pressure is measured in newtons per square meter. 1 Newton per square meter is Pascal, and it can be kilopascal or kilonewton per square meter, or it can be Pascal is equal to Newton per square meter, kilopascal is equal to kilonewton per square meter, megapascal is equal to meganewton per square meter. Now, let us say in a tank water is kept at a height of h, and it is point A, it is point B. At a point B, to get the pressure, this pressure is open to atmosphere, hence it is called as P atmosphere, that is equal to PA, and PB, here the pressure is PB. This pressure is equal to PA plus rho GH, where H is the water column or fluid column in the tank, and G is the gravitational acceleration, and H is the height of the fluid column. This can be delta P is equal to PB minus PA, that is equal to PA plus rho GH minus PA. PA is nothing but P atmosphere, that is equal to rho GH. This H with reference to some H, please remember, with reference to some datum, it is datum, or we can say you can take this as the datum. Anything you can call, nothing to, a reference can be anything. It can be earth or it can be sky. When the datum is taken, from the datum, let us say this datum let us not take for convenience because P atmosphere is there. Then let us say We have taken this as the datum. Above the datum, atmospheric pressure is there. Below the datum, water started exerting the pressure here. Water started exerting pressure. If the water column is 0 at P atmosphere, water column is equal to 0. At PB, water column is equal to H. Please try to understand this. Water column, here it is HWA, HWB. What is the water column at point A? It is 0. Water column at point B is H. This water column is measured downward. Why it is measured downward? Please remember this. This notation is very important. Please remember this. When you measure downwards the H, take it as positive pressure. Because as the height increases from rho GH formula, the pressure increases. H increases implies pressure increases. Provided H is measured downward. Then this rho GH can be written as rho G into H means HB minus HA, HWB. Instead of water, you can call it as fluid. Hence, let us drop the water subscript here. Let me rewrite it as HB. I have given an example only with water, just for your understanding. It can be HB minus HA. What is HB minus HA? That is equal to rho G into HB is H, HA is 0. Hence it is rho GH. This can be written as rho G into delta H. Difference in height. HB minus HA is nothing but difference in height. Do you agree to it? This is rho G delta H. That means difference in atmosphere is equal to rho G into difference in H. Okay. Delta H is the height of the fluid column. Above the height of the fluid column, it is atmosphere. Hence, the height of the fluid column above height of in the atmosphere is 0. Delta H is HB minus HA. Delta H. Delta P is PB minus PA. Please understand this. It's very, very important. Rho is the density in kg per cubic meter in SI units. G is the acceleration due to gravity on the surface of the earth. The average value of G is 9.81 meter per second square. We are not taking the G value above the earth surface and below the earth surface. It is on the earth surface. This is on earth surface. Be very, very careful while defining the quantities. Because below earth surface also G varies, above the earth surface also G value varies. Now, we will come to, now we have seen delta P, PA minus PB, PB minus PA, is equal to rho G into delta H, that is equal to HB minus HA. You see, You take a beaker in your hands, start pouring water in it. As the water column increases, that means from the water column, the bottom of the beaker, this is the beaker. In this first, this is H1, this is HB. Okay, weight will be lesser. If you same beaker, you are not disturbing, and water column is, this is H2, this is HB, the weight will be more. That means as here delta H is equal to HB minus H1, here delta H is equal to HB minus H2. As the delta H increases, as the delta H is increasing, that means the height of the water column below the atmospheric pressure, increases, the pressure increases. The opposite is also true. As height increases in the atmosphere, the atmospheric pressure decreases. That I will come to the next stage. Why I am giving much importance to this notation? Because the sign notation is very, very important in understanding the mechanics. Let it be classical mechanics, let it be machine designs, let it be mechanics of materials, let it be fluid mechanics. Wherever mechanics is involved, the sign notation, sign convention is very important. Now, delta P is equal to rho G into delta H. Up to this. For example, a beaker is there. Please try to understand. And this is the H. I start removing the water. I start removing the fluid. What happens? The pressure exerted by the fluid, let us say it is H by 2, let us say it is H by 4. The pressure exerted by the fluid will be reduced as delta H decrease implies delta P decrease. Now, that means we can establish a relation between delta H and delta P. That means delta P by delta H is equal to rho G. As per standard calculus, delta P by delta H, when delta H extends to 0. That means as we are reducing the delta H from H to H by 2 to H by 4, and we will make it delta H tends to 0, means what will be the shape of it? Almost delta H tends to 0. When it tends to 0, this becomes a regular differentiation, that is dy by dH. Delta P by delta H, this is the difference. Dy by dH is a differentiation. Dy will be an infinitesimal small, very small. Sorry, d by nahi, it is dp. Delta p, it becomes dp by dH. This becomes a differential equation. When it becomes a differential equation, the pressure is equal to delta P by delta H is equal to dP by dH. Delta P by delta H is equal to dP by dH. P by H, you can even call it as dP by dH. Delta P by delta H is equal to dP by dH is equal to rho g. Because P is equal to rho g H, it implies P by H is equal to rho g. This is a very important derivation we have done. Please understand this. If you want, you can listen to my lecture again and again. Try to understand this. You go back to your basic calculus which you have learnt in your diploma or degree engineering about differentiation and integrations. Now, you just see. There are two types of fluids. One is a compressible fluid. Compressible means what it is? Compressible means usually what happens whenever you exert pressure, as pressure increases, I am not talking about the ultimate pressures and what you call failure pressures. I am talking about 1 atmosphere, P atmosphere is there, 101.325 kPa, and 1.5 atmosphere, let us say 2.5 atmosphere, what will be 2 P atmosphere, 2 into P atmosphere will be 202.750 kPa. This is equal to 0.101325 MPa. This can be 0.202750 MPa. Whereas failure stresses will be 10 to the power of 6 MPa, very big. The failure stresses will be are of very big value. We are not talking about the failure stresses, ultimate strengths, ultimate stresses that we will be dealing in the mechanics of solids. Here, for solids, they are not fluids at all. When we come to liquids, from solids to liquids, solids, not fluids. When we come to liquids, next stage, as per in the order of crystalline structure, liquids are incompressible and gases are compressible. Compressible means when you apply a slight pressure also, the fluid tends to increase in volume. Volume is what? Density is kg per cubic meter. That means a slight change in the pressure that increases volume means density also subsequently changes. That means the density changes significantly with respect to a slight change in the pressure. In density implies a volume also. We are not changing the mass. Then the liquids or gases, let us talk about fluids, liquids and gases. When in case of gases, what happens? Like in piston also we can see, like in many thermodynamic based engines, what happens? A slight change in the pressure. What is ideal gas equation? PV is equal to nRT. When N doesn't change, R doesn't change and T doesn't change, what happens? PV is equal to constant. That is Boyle's law. PV can be represented when M is known. Then V is equal to, what is rho? Rho is equal to kg per. Now, what will be V here? V is equal to M by rho. M is constant. That means my P by rho is equal to constant. That means P is directly proportional to rho. A slight change in pressure is going to change the density. Rho is density. Whereas the ideal gas equation is not followed by liquids. Gases, hence we say that gases are highly compressible fluids. The example is air. Now, this equation is valid for all the fluids. Here in dP by dH, how we have measured? PA, from PA to PB we have come. PA is atmospheric pressure, which is 0. Or we took it as a P atmosphere, that is because everywhere atmospheric is there, that is taken as a datum is 0. Then PB is rho GH. We have height we have calculated from PA towards downwards. You see, dP by dH, we got this equation when dH is measured downward generally. Whereas when H is measured upwards in an atmosphere, here it is the earth, in an atmosphere, if we want pressure PB here, then we will be measuring H upwards. Something on the earth surface, we kept one beaker here, I am only exaggerating. This is H2. Here we have measured downwards for this equation. Whereas for atmosphere, when we measure in the upward direction, then dP by dH will be minus rho g. Hence, we conclude that atmospheric pressure decreases with the height from the earth's surface. You see, from here, density. Gases are highly compressible fluids. dP by dH is equal to minus rho g. And it decreases. And rho also changes with pressure. That we have calculated it as minus rho g. That means when rho is changing, definitely minus rho g will be changing and it decreases. How it decreases? Let us see in the next slide. You please try to understand the concept. Now, let's go for the incompressible fluids. Compressible fluid, air, we understood. Incompressible fluid means there is no change in the density or volume by slight increase in the pressure. There is no change. When there is no change in the density, then we'll write the equation as P is equal to, P at any point is equal to P atmosphere plus rho GH. This is for liquids we can safely write because rho G is not changing. You please try to understand incompressible fluids. The density does not change with respect to change in pressure. Liquids are incompressible fluids. The example is water. Now there is a slight homework I will give you. Name at least 5 liquids which are incompressible. Similarly, write 5 compressible gases on your own. From this, you try to understand. The meaning theoretically I have explained, practically you will understand from the books. Compressible fluids, the density changes significantly with slight change in pressure. Most gases obey the ideal gas, which I have told you. For atmosphere, the variation of pressure with the height can be found out from dP by dH is equal to rho G, where dH is measured downward generally. If it is plus, it is measured downward, and if it is measured upward in the atmosphere, as I told you, on the Earth's surface, this is the Earth, this is the radius of the Earth R, and this is the Earth's surface. From this surface, here it is P atmosphere. From this surface, if I go at a height, then P dash atmosphere is equal to how much? This P dash atmosphere is given by this formula. P is equal to P naught into U to the power of H by H naught. This is the height near the atmosphere H naught. At H naught is P atmosphere. This is equal to P naught. And at a height H, it is P. Then P at a height H from the P at a height H from the Earth's surface is given by P atmosphere at H naught into e to the power of minus H by H naught. This is the equation. That means the variation is the atmospheric pressure changes exponentially with respect to height from the Earth's surface. This is the equation. Please remember, and it is the law of atmospheres. Now, as a homework, you find out P at R by 2 H. H is equal to R by 2. Radius is R is the radius of the Earth. And if we go up to the R is equal to approximately, we can say 6,300 kilometers. If we go 3,000 kilometers above the Earth, what happens? Just try to find out. P at H is equal to R by 2. P at H is equal to R. That means you are going above Earth surface to the radius of the Earth surface. That also you find out. And you try to find out P atmosphere on Jupiter. And find the same values for P at R by 2 and P at H is equal to R. Try to do these exercises, then you will understand the meaning of it. And there is one question, very simple question, not a complicated question, asked in SSC JE 2024 that how the atmospheric changes as we go above the Earth's surface. Atmospheric pressure changes, atmospheric pressure decreases as we move upwards from the Earth's surface. Please remember this. How we move? Tomorrow if the same type of question is asked and alternatives are given, atmospheric pressure changes with height above the Earth's surface exponentially, linearly. As a square means it changes exponentially. Please remember this formula. It changes exponentially. That means any kind of question can be asked from this formula. If you remember this formula and understand this concept of pressure and compressible fluids and incompressible fluids and pressure at a point, you will be able to answer the SSC JE questions, direct questions in seconds. Please, this pressure is very important in fluid mechanics. Hence, I took an extra class as a under properties 3, extra class. You can treat it as an extra class for explaining the pressure. Because almost 3 questions I have seen, they have come from the point of view of pressure. And in this, I want to explain another thing also, vacuum pressure. I have explained you gauge pressure. I want to explain vacuum pressure also. This is the, 1 minute. This is the datum, that is P atmosphere. This is gauge pressure. Let us not take it as a P atmosphere. This is gauge pressure. This is P atmosphere. This is gauge pressure. And the total pressure is equal to P total, P atmosphere plus P gauge. If gauge pressure measured is a vacuum, if gauge pressure measured is a negative, if P gauge is positive, gauge pressure is measured by an instrument. If P gauge is positive, then it is called as a gauge pressure, the pressure measured by an instrument. If pressure is equal to measured by instrument is equal to negative, then it will be vacuum pressure. That means P absolute is equal to P atmosphere plus P gauge when it is positive. or P absolute. Here we can write it as P absolute, P total, P absolute. We can make it as P absolute is equal to P atmosphere minus P vacuum. You please remember these two things, which I have missed out in my previous class. Please remember. I have told you P absolute is equal to P atmosphere plus P gauge. Now, if P gauge is a pressure measured by the instrument, and if the pressure measured by instrument is negative, it is called as vacuum pressure. P absolute is equal to P atmosphere minus P vacuum. This you please try to understand. We'll do further detailed questions on pressure at a point, pressure measurements, and absolute pressure, atmospheric pressure, gauge pressure, then vacuum pressure. These things will further clarify because we are dealing with properties only here. I am not explaining them in detail. When we take up the next class, I am thinking, because I have taken this pressure as an important topic and I spent this much time, in the next topic I will delve into the topic of pressure measurement. Once we start doing some numericals, some concepts on pressure measurements, then we will be able to better understand what is absolute pressure, what is gauge pressure, what is atmospheric pressure, and what is absolute pressure. And if we do some numericals on calculating the atmospheric pressure at various heights and at various planets, on the surface of various planets, then we will be able to easily understand the concept behind it and it will imprint in our mind. Best of luck to everybody. This class I will conclude here. Be ready and read something before listening to the next class. I will be taking up pressure measurements. It's a very, very, very crucial and very important. The pressure measurement deals with vertical pressures, horizontal pressures, pressures on curved surfaces, and pressures, measuring instruments, how to measure the pressure, and also your manometers, liquids in the manometers, differential manometers. Will detail all those. Pressure measurements is a very, very important topic, both in the point of view of not only fluid mechanics, in soil mechanics also these pressure measurements will be useful to you. Whatever we are getting these concepts in the pressure now, those concepts will be useful for your calculations in soil mechanics. Automatically we are dealing with soil mechanics also. Many questions on soil mechanics, testing, pressure, soil and soil pressure, earth pressure, earth and dams, all these things we can discuss in the soil mechanics which go parallelly with it. You are learning indirectly soil mechanics also along with this fluid mechanics. Hence I have taken this as the first topic. After this I will be taking up environmental and then soil mechanics. So that the concepts are linked by one to the other. And next, as far as mechanical engineering is concerned, this pressure measurements, venturi meters, orifice meters, and these things will be useful even for open channel flows for civil engineering. And pressure measurements will be very much useful in case of the pipeline designs and pipeline flows and also for various property fluids. And this pressure is the important topic, most important topic. I spent this much time. I am going to spend another 2-3 lectures on dealing with pressure only, pressure measurements. Pressure measurements is very crucial. Very crucial topic, which I feel you people don't miss it. Please, if you want to study in a